Yeah, this is a presentation on all of chapter 2, actually. I know originally I was supposed to do about half of it, but I thought, like, what's 4 more slides? It wasn't just 4 more slides, but like I realized that last night. Anyways, yeah, first I gotta apologize because this is a lecture masquerading as a presentation. I have lecture notes, that's how bad it is. But if at any point, like, you have a question, yes, Jake?
Will we be getting the lecture notes after the lecture?
Do you want the lecture notes?
I want the lecture notes.
Well, you said they're lecture notes, so how am I supposed to?
Oh, yeah, absolutely. I'll put them on Canvas, yeah.
Thank you
Is this
very
going to be
much.
on the test?
Half of it.
Okay.
Yeah, only the
Do
important
we know
stuff.
which half?
No, it's kind of like a give or take. But yeah, if you have like a question, do what Jake did, raise your hand, and if I don't like you, I'll probably ignore you, and then just talk over me. I'm not kidding, like interrupt me. I know professors say that. and you
Thanks
don't
for
believe them.
complimenting me. Thank you.
What'd you say? But yeah, no, that's about it. So today is just chapter 2, which isn't anything like super new. It's just a lot of cool niche stuff, but conceptually not too out there, which is why I took it upon myself to make it conceptually out there, because otherwise it's not entertaining. So this is Gravity's Fatal Attraction, Black Holes in the Universe, Chapter 2 presentation for Physics 2011, Ampersand Gateway Expeditions into Black Holes, by me. So, that's not supposed to happen. Okay, yeah, this entire chapter was about stellar evolution. If you can like just boil it down into one thing, it's about how stars are born, how they live, how they die. Oh I got ahead of myself. Yeah, that's a nebula. Presumably where stars are born just takes a lot of gas and dust from gravity and time. They live, that's our sun, and eventually they do go boom, they do die. That's the Crab Nebula. Looks super pretty, result of a supernova, which we'll get into later. But first, we gotta get some things out of the way. We gotta talk about bad diagrams. I really don't like this. This sucks. Why? Because it's like cool, it's fun to be like, oh, this type of star turns into this type of star. But like really, what is going on here? You know, this was fun when I was like 7, but it's not like there are just 4 types of stars. And there's also this weird like perspective/size thing going on, where it looks like the stars are getting close to you, but it also looks like they're getting bigger. And also, what do the colors mean? Like at all. There's really no explanation. So there's only so much you can do with these graphics. You got stuff like this, which is like, it says more, but what the hell is going on? Like, I get that it's trying to be like a life cycle type deal, but they just slap a bunch of different images. The black hole is a higher resolution than like the supernova, which comes from like a different image than the whatever protostar thing. This is a bunch of different PNGs slapped together. We can do better than that. There are some good like flowcharts out there, but they're complicated. Not that this presentation isn't, you can only do so much. And they're pretty, they look good, but you know, we can do better. So first, gotta get something out of the way. In terms of what kinds of stars are out there, we sort things through this system called stellar classification. And it's weird. There's a lot of history behind why it is the way that it is. And it's a shame because we're not gonna be going over most of it. But they were initially classified by like the absorption lines of what kinds of elements were in stellar atmospheres. And a lot of it, like at least the system that we currently use, was put together at Harvard by, not this guy actually. So this guy, Edward Pickering, he kind of led a team in like 1910s, 20s, at Harvard called the Harvard Computers, who were actually the people that did the work. They were all women that either worked for Pickering, like one person used to be his housemaid, and then ended up like revolutionizing astronomy. These are the people that kind of set the foundation for what modern astronomy is in terms of the observations that they did, the cataloging that they did, and just describing what our universe actually looks like. So, you know their names type of thing. One like very famous example, Henrietta Swan Leavitt. She was she tried to go, variable stars. There are certain stars out there that pulsate with a certain regularity, and she basically characterized that pulsation with their luminosity. And by using that, you can use, yes?
Is it the same as pulsar, or is that?
No, different thing. We'll get into
Still
that.
pulsing different.
Still pulsing, different mechanism.
Yeah.
It's just a star that kind of like grows and shrinks through very complicated things that we do not have the time for. But it is a star that goes through this like pulsating mechanism, and it's like linearly correlated or something, I think, with how bright the star is. So you can actually measure how long it takes it to pulsate. You can figure out, oh, the star needs to be this bright, and I see it as this bright, which means it must be this distance away from us. So it's like an essential rung in something called the cosmic ladder, which is how we measure distances to specific things out there. And actually, Hubble, Edwin, I don't know his name actually, Edward Hubble used this to figure out how far the Andromeda galaxy was away from us, because back then in like the 1950s, we thought everything was just the Milky Way galaxy, and then he found out, oh shit, this thing is like 100 billion light years away or something, or 200, I don't know. Like it's a crazy distance away, and that kind of revolutionized and paved the way for like modern cosmology and where we think the universe is today. And he says that like Henrietta Swan-Leavitt deserved a lot of credit, which he didn't get at all. There was a point where a Swedish mathematician was like, oh shit, this person deserves a Nobel Prize, but you have to get nominated by someone else. So he nominated her, he sent her a letter, and then he got a response back that says, hey, this isn't Henrietta Swan-Leavitt. Thanks for the nomination, but unfortunately she died of stomach cancer 4 years ago. So she never got the Nobel Prize because they don't do that posthumously for reasons. And so generally considered forgotten during her time, but since then the like AAVSO, which is the American Variable Star Observatory or something, and other articles have been trying to get her more, her name more recognized. Then there are other people like Williamina Fleming, who did like a crap ton of just like categorization and cataloging and stuff like that. That kind of set the ground for the amount of data that we need to actually classify these stars. But who we really need to talk about today is, oh yeah, these are photos of them. Leavitt's on the left, Fleming is on the right. Who we really need to talk about today is Jump Cannon, the GOAT, because she kind of actually defined what our current system looks like. This is a quote from a Smithsonian article. I'm not going to read it. I'll send the slides or something. But the point is that she developed the system. Her, Pickering and other people got credit for it. She was never recognized for it. And they don't even name it the Cannon classification, unlike everything else in science where it's named after the person. They named it after Harvard, because women, they don't get the credit. I'm a feminist, you guys. But anyways, this is what the actual classification, spectral classification, looks like. The reason why it's in such a weird formation is because initially it was defined by spectral lines, but then they were like, hold on, we should do this by temperature instead. So we did it by temperature instead. And there are actually two different ways to like remember the weird ordering of this. The main one was, oh, be a fine girl, or oh, be a fine guy and kiss me. And then that was deemed a little insensitive, so then I think the current one is, our bright astronomers frequently generate killer mnemonics. If you remember, mnemonics is spelled with an M. Other than that, yeah, a lot of people know their names. This is what we currently use, and we'll get into why this is important in a moment. Low-key, I just wanted to put this in the presentation. But why did I include this?
Oh, yeah. An example of a better chart for the star things? Are you?
Yes, I'm building up. I'm building up. We'll get there for sure. We'll get there. So another quick tangent: spectroscopy. This was a section in the textbook, so I'm actually like justified for including this in there, but we've done this before, we've seen this before. Transmission spectroscopy, Tansu talked a lot about it in the exoplanets class. Basically, certain molecules, certain atoms, both absorb and emit certain wavelengths of light, and so we can detect what atoms and elements and compounds are in a star, or in a nebula, or in a planet's atmosphere by seeing what kinds of light come through. But there's more to this story. There's something called black body radiation, which is kind of important to okay, yeah, we already did that. But there's something called black body radiation, which is kind of important to understand for the sake of, sorry, I have hair in my mouth, for the sake of like spectroscopy and everything. And the idea is that everything that has some kind of temperature is radiating light. This includes you, but we aren't radiating it in the visible spectrum, at least not a lot of it. And that's why you can see people and things and alive things in infrared. Right? Like IR cameras can see people, oh, I should have included a photo, but can see people like glow in the dark, as long as you're looking in the infrared wavelength. But as you heat things up, like if you heat a human up, they melt. But if you heat like a piece of metal up that can actually take it, then it glows like first a dull red, then an orange, then a white, and then maybe even like a blue-white. You might be asking like, why not green if it goes through the entire spectrum? And the answer is that by the time that it peaks at green, which is like this 500, can you see that? Yeah, 500 Kelvin, it's kind of uniform over all the wavelengths, and so it glows white instead of just green. Yeah, and emission absorption just depends on certain properties of the molecule, certain properties of the atom, which we didn't get into last class, but we will get into right now. So pull up those calculators, you guys. It's time to do a little math with the Rydberg formula.
Nah.
Okay, fair. But yeah, this is basically a formula that defines for a atom. We don't do compounds because that's complicated. For an atom, what specific absorption emission lines will we detect? You can actually predict what they are based on this formula. So this is how you use it. Lambda, wavelength, nanometers, just do that. Rydberg constant, you gotta just know it. Z is the atomic number. We're just gonna deal with hydrogen for now. NF and NI are the numbers of the shell that the electron jumps up to or jumps down to, or the orbital, whatever. So choose two random orbitals that aren't the same, and go ahead and calculate whatever the lambda should be, like the wavelength should be, and let me know what you get. Try, if you can, see if you can get an answer between 300 and 700 nanometers, which should be around the visible spectrum of light. Let me know what you guys get.
Yeah.
Nice. Sounds. We have to use hydrogen?
Yes. Well, I mean, you could use a different one, but I prepared this for hydrogen.
Oh, I didn't know if that's one of the things that we were picking.
Let's use hydrogen. We should just piss them.
You think you'd be upset?
I'd be very upset. I don't know what you're
Shoot,
talking
you weren't
about.
supposed to hear that. I'm shoot, you weren't supposed to hear that.
Do you think if I send you something over text that it would pop up on your computer currently? I haven't done it.
Not anymore.
Damn it. Because I was going to send you an infrared picture.
Oh, that would be cool. Yes, I know.
Yay. But now it won't.
Not true.
Is it 10 to the power of -2?
Um,
1.097. I'm trying to read it from
Yeah.
here.
oh, yeah, sorry. That's 1.097 times 10 to the negative 2 in inverse nanometers. Yeah.
What were the shells?
You can choose like a small number, like 1, 2, or 3, ideally.
Okay.
Like hydrogen orbitals are typically small because it's just the one electron. There are spectral lines, but the more absurd orbitals you choose, the more absurd the spectral lines will be. And so it's probably right, but like ideally try and get something within 300 and 700 nanometers.
I got 656.
Perfect, 656. Does anyone else get 656
Yeah.
for whatever they chose? Did you choose 2 and 3 as your orbitals?
I chose 2 and 3.
All right, perfect. You should get about 656.3 nanometers, and that is,
Did I get that?
oh, really? Maybe I got it.
I should have that.
And that is the wavelength of hydrogen alpha. This is our sun and hydrogen alpha. It's a very, very useful wavelength that we use like all the time. A lot for like, you guys remember radial velocity? You know, the delta and lambda. Usually it's determined by measuring where the hydrogen alpha line
It's
moves.
not popping up.
Dang. Oh, because I killed the...
Yeah, you're...
Okay, anyways. If you chose some other stuff, then you'll get other answers. These are all the different kind of the different groups of spectra that are out there. If something drops from a higher orbital down to 1, it's called a Lyman spectra, or it's in the Lyman spectra. If it drops down to the second orbital, it's the Balmer line or Balmer region, the Paschen, whatever the other names. And you know, 656 is this hydrogen alpha line that you see right here, but if you chose some other absurd numbers, then you probably get other absurd lines. These are what the other families actually look like. Okay, we're almost done with the introduction. In terms of the actual like diagram that I was like building up to, we're gonna use something called an HR diagram, or the Hertzprung-Russell diagram. I forget if we went through this last class. We probably did. We went through a lot of things last class. But just like a quick refresher, it's a diagram of temperature by luminosity of a certain star. And so temperature, as we saw, is kind of the same thing as spectral class, just because that's how we define spectral classes. And then the luminosity is determined by a couple things. It's determined by the color, for one. Like blue stars are more luminous than red stars, because blue is just more energetic. But also the surface area of the star, the general like temperature, and also the brighter a star burns, the shorter its lifetime is, which is just like a fun kind of side effect of the actual luminosity. So generally, if you haven't seen an HR diagram before, pretend you haven't seen one, you might assume that like, oh, stars are kind of uniformly distributed in terms of the relation between temperature and luminosity. Like there are bright yellow stars, there are bright white stars, there are bright green and blue stars, but there are also dark blue stars, and there are also dark red stars, and there are bright red stars, whatever. And the answer is no, that's not how it is. Because there are very defined, populations of certain stars that follow certain paths within the actual HR diagram. So generally, most stars that go through their life are considered on the main sequence, which is like an inverse proportion between temperature and luminosity. Our sun is on the main sequence. It's like right there in the middle. If you can see it, it's considered a yellow dwarf because it's small and yellow. Astronomers are fantastic at naming things. But then you also get like giants, which are large stars. Some are blue giants, like Rigel. Some are red giants, like Betelgeuse, which is going to go supernova in like the next couple centuries or so. And then you also have white dwarfs, which aren't stars technically, but we can include them on the on this diagram because we should talk about them anyways. So there are a couple different HR diagrams out there. Of course, we're going to use this one to just model where things end up. And of course, there are also stars that fall outside of this classification. There's this weird area called the instability strip. You know how I talked about variable stars? A lot of variable stars fall in this, like Cepheid variables, are Lyrae variables. We're not going to talk about them because this lecture is long enough. But basically, yeah, HR diagrams. And we are going to kind of track a star's evolution using this diagram. So just to be clear, this is about how the star, changes its own structure, how it gets hotter, how it gets colder, how it gets larger, and not about its actual movement through space or anything. So this is just the evolution of a star on this diagram. Just to put that out there. So, there's a lot of things. I'm gonna take a quick Orion break. Like the textbook does, it just hits you with a full page Orion Nebula photo. For no reason, I think it just wanted to do that.
It's pretty nebula.
It's a really pretty nebula. That's a great point, PJ. How would you guys like to see this nebula with your own eyes? It's actually really easy. Oh, thank you, Yaga. It's actually really easy because this is one of the brightest and largest nebula out there. To put it in perspective, this is a photo that I took with my phone, iPhone camera of Jupiter. You can't see it, you can't see much. It's blurry, it's hazy, there's a lot of stuff out there, it's not very zoomed in. The only reason you can maybe tell it's Jupiter is because there are 4 dots around it, and those are its 4 Galilean moons. With that same telescope and with that same phone, took this photo of the Orion Nebula. Which is it's not Hubble, but it's pretty good. And you generally see something a little like that when you're looking through a telescope. So if you have the chance, this is for sure something that if you go to some person who has a telescope set up in their backyard, or if you go up to the observatory, Rami Observatory shout out, there's an observatory sitting on top of Crow, by the way, if y'all weren't aware. And it's open almost every night, right? Every night.
I mean, every weekday night.
Every weekday night, as long as it's not cloudy or something. But yeah, you can see this really easily, and it's super easy to find because it's so damn bright, because this is Orion, y'all know Orion, hopefully. If you look up after 7 p.m., you'll see it in the sky. It's one of the brightest and easiest to find constellations. It's that one. In terms of how to find the Orion Nebula, also super easy. This is the belt. It's the 3 stars across Orion's belt. And if you look right under it, towards his feet, there are these other 3 stars, and the middle dot in those other 3 stars is the Orion Nebula. Even in this photo, it's super damn bright. And so you can just kind of faintly see it on WashU campus because city, light pollution. But if you have a chance, look for this one. Anyways, just wanted to share that one. Now backtrack to it. Stellar birth, how stars are born. First, this is our first introduction to using the HR diagram. You can see the main sequence as this line going through it. But essentially it starts out as this huge cloud of gas and dust and stuff that isn't really doing anything except sitting there and getting closer and closer together until finally it gets onto the main sequence. It gets onto the main sequence and it starts fusion and all of those things. So we would visualize that by this super dark and super red and gloomy, but huge nebula almost, cloud of gas and dust, etc. That kind of condenses and gets smaller and maybe and a little hotter, but less luminous because it's smaller as it migrates its way onto the main sequence. So during this time of formation, this is where planets start forming, protoplanetary disks and all that stuff. And eventually they migrate onto the main sequence. if a star doesn't have the critical mass to start fusion, it ends up like somewhere down here. If it, the brighter it is, the more mass it is, it gets up here. If it doesn't make it, it's a failed star. It's a brown dwarf, and those just kind of sit there. Like they're not strong. They're not strong enough to start fusion, but they're also not weak enough to just like fly apart. So they just kind of sit there and fizzle out eventually over like trillions of years. Jupiter is pretty close to being a brown dwarf actually. If it had a bit more mass, I don't know exactly. I think 10 times more mass or so, it would have been a brown dwarf. Like someone feel free to correct me. But anyways, in terms of what it takes for a star to actually grow and live, etc. If y'all remember the beautiful presentations from last week, it's all about equilibrium. Specifically, it's about something called hydrostatic equilibrium, which is just a fancy word to say like fluid-like things being in equilibrium, and everything that's vaguely spherical is in hydrostatic equilibrium. This includes planets, it includes stars, this includes neutron stars, it includes white dwarfs. The only difference between these objects is what exactly that internal pressure is that is outside against gravity. So for planets, it's like the own structure and support and stability of the rock. For the stars, it's nuclear fusion, which we'll get into. And for neutron stars and white dwarfs, it's weird quantum mechanic, hand-wavy stuff, which we'll also kind of get into. In terms of how fusion actually works, you don't have to like know this, but it's nice to see a diagram for this. Unfortunately, it's not as simple because nothing ever is as two hydrogen atoms coming together to create a helium atom. It's something called the pp chain or the proton-proton chain, but I'm going to call it the pp chain because it's funnier, where you essentially need 6 protons in at some point, and then outside you get an alpha particle or a helium nucleus and 2 protons along with some other emission stuff. So first two protons come together, or hydrogen nuclei, same difference. And this is like the defining step for what it takes fusion to occur, because this takes so damn long to happen. It takes like 1 billion years on average for 2 hydrogen atoms to wander close enough to each other. Even in the like intense pressure of the core of a star, this is what really puts the limit on the rate of fusion that happens in any star. So the nucleus or the proton turns into a neutron, and because you gotta conserve certain properties like charge, and also certain other weird properties like lepton numbers, which we're not getting into. It emits 2 particles. One is a neutrino, which does nothing almost, and one is this beta particle, which is an electron, except for the fact that it's positive. So it's a positron. And a positron is antimatter. It's an electron, except it's positively charged. Do y'all remember what happens? I'd say remember like we ever learned it. Do y'all know what happens when antimatter hits matter?
It cancels out.
Almost cancels out. They immediately get turned into they blow up. It immediately annihilate each other, turn each other into photons, gamma rays, etc. And so, since that positron is in a star, it immediately annihilates and turns into gamma radiation. The neutrino maybe gets out. There's like a 10% chance that it hits something and transfers its energy, but typically the neutrino gets out. Then, over the next second, another hydrogen atom comes by, smashes into it, lets go of a gamma ray, which is just a photon. And then, over another 1 million years, the 2 helium atoms come together. 2 helium nuclei, helium-3 nuclei come together, form the alpha particle, and let go of 2 protons. So, more math time. This recipe is equals mc squared. That's it. Basically, the output is less massive than the input somehow. The question is, how is that possible? And that's why I'm telling you to do all this math. Because helium atoms have certain masses, the protons have certain masses. My question is, how much of this mass is actually lost in the form of radiation, in the form of other stuff? This is not a rhetorical question, I'm actually asking you. Do the math, you guys.
About 3.
I agree.
About 3?
Yeah.
That's fair, that checks out, I think. Yeah. Does anyone have an answer?
Stop looking at us like that. I don't like that.
Basically, you just want to.
So we're not including the 2 protons, the arrows.
That go out.
They go out.
Yeah. So basically, it's just
So we start with 4 hydrogen, we end with 2 hydrogen and 2 other things.
You start with Yes, you start with but it's actually not just hydrogen. Specifically, it's a helium atom, and that's important because there's some like weird nuclear physics stuff going on. That means a helium atom is less quote unquote massive than a proton. So let me know if you guys get like a reasonable answer for this. But basically, how much mass are we losing after this reaction? Yeah. Wait. Hold on.
We don't have the mass for hydrogen.
This doesn't add up actually. Did I screw up the numbers?
Yes.
That's a shame. Okay, well, anyways, it's a certain amount. I was gonna do a whole thing where it's like, how
You
many
didn't
reactions?
even give us that number.
What?
You didn't give us the last number clearly. That was the issue.
What was the last number?
The N one.
Oh, that's the mass of the sun.
Yeah,
I was
we did
gonna
that, right?
say that, yeah. That one is right, I know that one's right. But anyways, I was gonna do a whole, like, how many reactions are happening in the sun per second to create its, like, luminosity? What percent of the sun's mass is being obliterated every second? But I screwed up the numbers, so we're gonna forget all that. Anyways, this is where, like, the bulk of the lecture is, which is great because we're already half an hour in. This is stellar death, what happens when the fuel runs out, when you're out of hydrogen. And it depends, actually. There are like three main areas that we're going to go into. One is like what happens to low mass stars, which is 0.1 to 0.6 times the mass of our sun. And they turn into like a red white dwarf. And it's not that interesting. What happens to a mid mass star, which is about the mass of our sun, up to like 10 times the mass of our sun. And it is a lot more interesting, but it's also hella complicated. So we're going to go through that one as well. And then finally, high mass stars, which is like ironically a little less complicated in a sense. Which is like larger than around 10 times the mass of our star. You might find different numbers for this floating around because this area of astrophysics is determined by like how good our computers are. Because it's all simulations. We don't get to see supernova happen very often, and especially close by, which is good because we'd be annihilated. But that being said, we don't have a lot of like empirical data for this, so a lot of it is defined by our simulation work. And yeah, if it's a high mass star, it turns into a neutron star or a black hole, which is why we're here. But anyways, first, in terms of low mass stars, it takes a while. It takes a really long time because, as we talked about, a higher luminosity means it burns through its fuel faster, but low luminosity means it hangs around for a damn long time, which is like, do I have a number here? I don't have a number here, so we're gonna get into the number on the next slide. But anyways, the point is that something weird that happens with low mass stars is they have something called a convective interior. If you remember like convection and conduction from 8th grade geology or whatever you guys learned it. Did y'all not like learn this? I remember everyone knew about this except me.
Oh, that's a geology class.
Y'all know like what I'm talking about, convection, conduction. Like, that was a thing. Like, that was a, yeah. Okay. Anyways,
like earth science.
Point is that like hot stuff at the interior of the star gets pushed out because it's less buoyant, something or the other. And basically the inside's constantly, there are a lot of convection currents going on, so new hydrogen is constantly falling into the core to replenish the fuel cell or the fuel that's already there. And because of that, there's no helium, inert helium core that just sits there in the center, like piling up. It always constantly gets recycled. And because of that, the star goes through its entire fuel of hydrogen, like all of it. And because of that, it stays alive for so damn long. Like our current estimate's 6 to 12 trillion years, which is like nothing compared to how old the universe is. We have to wait for 1,000 times the age of the universe to really see red dwarfs do this thing. Which is like stupid ridiculous. But anyways, it's like a very slow death. They just kind of slide into obscurity. Now, in terms of what actually like happens, like how it looks, this is when we're actually going to use this HR diagram that I spent 20 minutes building up to. So you can see our red dwarf is like all the way down on the bottom right. It's really hot, it's really red, and it's really dim because it doesn't have a lot going on for itself. First, like as it cycles more and more and more hydrogen, helium, this is towards the end of its lifetime. Eventually, it gets smaller and smaller. It moves up a little, it gets a little hotter, gets a little brighter, gets a little smaller, and eventually it just goes straight and turns into a white dwarf. And then it just kind of sits there as a white dwarf because of the whole neutron degeneracy thing. There's no more fuel to burn, which we'll get into. Electron degeneracy. And then as a white dwarf, it just kind of fizzles out. Like, it takes a while to fizzle out. And it just fades, it just dies. Yeah, what's up?
What happens to a white dwarf when it fizzles out? Because we know they have to fizzle out, but like it's still going to be there, right? There's no fusion or fission or anything happening, so they're not losing mass. Like when a white dwarf is done, is it essentially like a really big, really heavy gas giant, or like?
Yeah, not a gas giant because it's still dense. There's still a lot of matter there, and it's still under degeneracy pressure because gas giants just aren't massive enough. White dwarfs are still really heavy, like half the core, our sun's 2 times 10, it's like a nonillion kilograms or something. I don't know, some number like that. But point is they're really heavy, but they do just kind of sit there. I don't know the details, but as far as I'm aware, they just keep radiating like thermal energy until it's a black dwarf, which is just kind of a chunk of gas that's there. Yeah, what's up, Ashley?
I was just gonna say, like, that's like what we like suspect, but like we haven't actually been able to observe that.
Yeah.
Like, just how long it takes.
It's just like like the universe isn't old enough for us to see this happen.
Yeah.
The universe isn't old enough to see these stars form and then die. So we're still kind of waiting on that. But that being said, red dwarfs are considered the most prominent, or not prominent, frequent, what's the word for something that's like there a bunch? Prolific, sure, yeah, absolutely. Most prolific form of star. We think that they're all over the Milky Way, but we can't see a lot of them because relative. Anyways,
Abundant.
Abundant, yes! You're so right, okay, abundant. That's it, they just kind of died. But now we get into the more complicated stuff and the more interesting stuff. Mid-mass stars, that's us, so whatever happens, whatever you learn in the next few slides is what's going to happen to us in like 5 billion years, which is a shame because we won't be there, which is probably good that we won't be there to see what happens. It's insane. But anyways, that's where we are. We're G-class spectral type, G spectral type, yellow dwarf because we're yellow and small. And basically, we keep burning until the helium, or the hydrogen in the core runs out, and then helium starts building up, inert helium, because we just don't have enough mass, enough pressure, enough temperature at that point to start helium fusion, because that takes another like huge step for that to start happening. So instead, it's just an inert core surrounding, or just starts building up in the middle. And because it's an inert core, it kind of pushes the other layers outwards. So then hydrogen starts fusing in a shell around the helium, quote-unquote nucleus, helium, quote-unquote core. And as the hydrogen starts fusing, it puts more pressure on the helium core, which in turn increases fusion rates, which increases temperature, which increases pressure. And we almost have like a runaway thermal reaction as the hydrogen fusion gets faster and faster and faster. I'm simplifying a decent amount here, but a lot of the outer layers, yeah, what's up?
Oh, so just trying to clarify, so the core itself is getting like more compact, but this outer layer is the one that's expanding?
Well, the core isn't getting more compact, it's just getting larger. Because the core supports itself at a certain density due to its own like degeneracy pressure, which is just how like close the helium atoms can get together without fusing. They're still pushed apart by their own like strong force, which we'll kind of get into later. But the helium core just keeps growing because more hydrogen turns into helium, but then there isn't enough energy for that helium itself to fuse. So it just kind of keeps building. But because it keeps building, the hydrogen atoms that keep wanting to do fusion end up doing it on the surface of that helium core, and so it creates this spherical shell around the inert core where all the fusion takes place. Okay, outer layers get pushed out. This is where we start going from a subgiant into a red giant. The outer layers are pushed, starts obliterating stuff that's near us. What's up, Ashley?
I was just say, like, the way that it's worded, it sounds like you're saying, like, it first broke the hydrogen, then the helium, as if it's like a series of steps, but I didn't think that was how it worked.
Kind of it is.
It is?
If for heavy enough stars, it is. For our sun, this is like when it starts dying. This is in the last billion years of its life, about.
Okay.
And it starts running out of hydrogen in the core specifically, and the core is just defined as the place where the fusion is happening. So that we have a lot of helium buildup, and then the outer layers start getting pushed away because the hydrogen fusion in the spherical shell kind of pushes it outwards. And the helium core kind of in a way makes the fusion happen faster. Details. Anyways, star expands, it starts burning faster and faster in terms of what that actually looks like. I'm missing a transition, but whatever. It gets larger, it gets brighter, but it also gets redder. And so we end up as a giant, subgiant or red giant. And at this point, we have a helium core, we have an outside, and we have a bunch of stars. Now, at a certain point, it gets too hot. Helium flash. This is a point in a star's life where basically, actually, you're right, the next step happens, and helium, there's enough pressure and temperature, etc., for the helium to start fusing. So all of a sudden, amidst the helium core folds under its own pressure, it fuses into carbon and oxygen on a timescale of like days, like all of it. And there's enough pressure for this to happen in this moment or over this course of days, about like 10 billion, how long is it? 100 billion times the normal star's output is burned at this moment, which creates a huge amount of pressure, huge amount of energy, which is crazy because nothing ever happens, nothing really happens. And all the outer layers absorb that energy output. So we don't observe helium flashes, but they just happen in every single like our best simulations. So we're pretty sure this is what happens. So the star from the outside, no reaction, not really. It's just chilling. It keeps doing red giant stuff. But at a certain point, the helium fusion slows because there's no longer that like inert helium core that's like super hot and pushing on it. And because of that, the star shrinks back again. And it goes on something called a horizontal branch, which is kind of, from the red giants back onto the main sequence. There are some weird cases out there. We can't talk about that. There's only so much time, and also low-key, I didn't understand it. So we're gonna ignore it for now. But for now, we see like our star turn into a giant, and then after that, it migrates back towards the main sequence as a horizontal branch. It gets bluer. Yes?
Is this first of all, is that hydrogen fusion or helium fusion slows?
Hydrogen.
Hydrogen.
Helium fusion starts.
Okay.
It starts fusing the helium, but the hydrogen, the amount of helium was pushing hydrogen fusion.
Okay.
And because there's no more inert helium, like a lot of that pressure and temperature is kind of released, and so the hydrogen fusion slows, which causes it to shrink back down.
So if this happens over the course of days, how long can we expect this helium flash to last? / how long does like that part of the stellar evolution last in this context?
Yeah, so the helium flash takes days to happen. It's just the description of what happens when the helium core finally starts fusing and goes through and enters its next phase. So it's what happens when a giant star moves onto the horizontal branch. This is probably, I don't know if Betelgeuse is a supergiant, so it might be doing something different. But if it's a giant, then we might see this happen, like real time. But anyways, yeah, the idea is that, this is, I want to say 100 billion years left. It's getting like soon for the star to die. Yeah, what's up, Ashley?
I was about to ask, so is this suggesting then that like either helium is harder to fuse or its fuse is less powerful than hydrogen? Because hydrogen seems to be the thing that's supporting the star main sequence.
Good question, both.
Okay.
So helium takes more energy to fuse and also outputs less energy than a hydrogen fusion, relatively speaking. So it's easier to fuse hydrogen than other larger atoms, effectively. And more importantly, it produces a lot more energy output to fuse hydrogen atoms than other stuff. That's fair. We'll get it. So there's more stuff there that we'll get into in like another dozen slides in terms of how much how much energy output there is for each fusion. There's a lot left. Yeah.
Real quick then. So if the sun is taking that path sort of up to the horizontal branch, why do we not see more points on the graph?
Because it's so fast.
I see. So it happens to very many stars, but there at any one given time there are not a lot of stars doing that.
Yes, exactly. Because it's so quick, like
They just like
yeah, this is very related to how like the time scale question. At what scale is this happening? Main sequence stars will stay on the main sequence for billions of years. Giant stars will stay there for, I don't know, actually. I don't want to make up numbers because I totally could do that, but I'm actually not sure. But generally, there are two things that drive like the population densities that you see, and one is just how many of them are there, but also how long do they stay there, right? Because we're only seeing stuff in like a certain snapshot of time, these surveys. So that's a good question. Yeah, the reason is because it takes less time to happen, and directly after this, there's going to be another weird, movement of the star. So this is nowhere near the end, or it's like kind of close to the end actually. It's almost to the end. There's like 2 more steps. So as we just went through, as we just said, you know, there was a helium core that was inert, and then hydrogen was fusing outside of it, and then the helium core started fusing. What happens then? What the helium core fuses into is carbon and oxygen. So we have a carbon and oxygen rich core, and then we have a helium shell around that, and then we have a hydrogen shell around that. And the helium and hydrogen are fusing, but the carbon and oxygen, there just isn't enough mass for them, or there just isn't enough outwards gravitational pressure for them to start fusing. Yes?
So this means that the hydrogen and also, so does the hydrogen and also the growing carbon-oxygen core, are both of those sort of required to drive continued helium fusion?
Yes.
Okay, so it's sort of the same mechanism as before with the shell growth.
Exactly. So we just do this again,
Yeah.
right? Yes, what's up, Ash?
I'm so sorry.
No, you're good.
I was going to say that, like, if the hydrogen is fused at its core, right, and it's going until that basically runs out, that energy runs out before it starts fusing helium, then how is there still hydrogen, like a hydrogen envelope, and then like a layer of hydrogen, like, and it kind of, you know, like it gets
Yeah. No, that's a good point. I should have been more specific. So the hydrogen core is specifically, first of all, it's maybe half of the star's mass. A lot of the star's mass is in outer layers, but those outer layers don't experience fusion because there's not enough pushing on them gravitationally to drive hydrogen fusion. So there's only fusion in the core because you have the entire star's mass pushing on you to drive that fusion. And so that's why the hydrogen envelope around the core doesn't experience that same fusion mechanism because there's not enough external pressure.
I see.
And then the closer you get in, the higher the density is, the more pressure, heat, temperature, and the easier it is for fusion to occur. And so the core, it's a little hard to like really draw lines. This isn't what a star actually looks like. It's far more of a gradient. But there is a certain area of the star where we say, okay, that's where fusion really happens. That's where the temperature and pressure is high enough for fusion to really occur. And generally, most of the mass of the star is there because it's so dense. Yeah.
Is the carbon oxygen core, is it really like they're both there together, or was it just like over the course of this like gradual evolution with mostly carbon and oxygen like transfers, or is it kind of like a melange? Like,
No, good question. I think there's mostly carbon with some oxygen because carbon is easier to form than oxygen. Helium does fuse into both through a process called, there's something called the CNO cycle, carbon, nitrogen, oxygen cycle, where those three nuclei just keep like forming into each other, releasing energy. But there's also something called reverse alpha decay, I think, which drives the carbon and oxygen process. Correct me if I'm wrong, look it up, I don't know. I can't talk about that. And I don't want to like bullshit you. So yeah, point is carbon oxygen core. And there's nothing else other than carbon and oxygen at this point because there's not enough fusion for them to do anything. But yeah, it is both of those things. Okay, yeah, and then we have our shells. It gets on, so before we had something called the red giants and then on the horizontal branch, and now the star gets on something called the asymptotic giant branch, which I'll show you what it looks like in a second. But yeah, eventually, finally, we run out of fuel, the hydrogen stops burning, there's not enough to push the helium, it's not burning. And then the hydrogen helium shells kind of expand because there's not enough fuel for them to keep like fusing and stuff, and so the internal pressure becomes too much. And gravity, or not gravity, I'm gonna be honest, I don't completely understand the mechanism for how the outer layers push out. I understand that they expand, like get huge, but I don't get how gravity doesn't win completely. I understand that there's a lot more that I kind of glaze over here, gloss over here, and there's gonna be even more of that in the future, believe me. But if you ask me a question, I wouldn't be able to satisfactorily answer, so don't ask me anything. Thank you. Yes?
I think the only difference is that sometimes the energy is more produced in some shell than in the inside, because the inside, as you said, is not hot enough to fuse,
Yeah.
so it's just sitting there. And if the energy input is like in a shell instead of the center, this kind of changes all of the
Like
profile,
the dynamics of
and then it gets really big. But just because it's kind of, once the center also burns and some more massive, it becomes small again.
Okay.
So it's kind of where the energy is generated, and that changes the profile.
Okay, that makes sense. Yeah. Yeah, so like when it's a spherical core, all the energy is like radially outwards, but when it's a spherical shell, it goes in other stranger directions. Okay, that makes
The
sense.
temperature profile depends on how much of the energy is absorbed by the outer layers, and if that is quite a lot, then it kind of gets bigger and gets pushed out.
Sure. Okay. Good to know. Yeah. Right. Oh, yeah. So where were we? We were at this like place right after helium flash. It's a little colder. It's a little bluer. It's a little smaller. But then we go up to our supergiants. The asymptotic giant branch, and then this is a very short period of the star's life because at this point everything gets blown apart, and eventually no more fusion. The outer layers get pushed away. The inner core just kind of sits there. And then the core shrinks and shrinks under its own gravity with no fusion to support it, until finally we hit something called electron degeneracy. Weird quantum stuff. I'm gonna go into it really shortly because the textbook already did it, and quantum mechanics, so that's like a whole unit, or that's like a whole class, so we're not doing all that. But there are two things at play. One's called the Pauli exclusion principle, which just says that certain particles, classes of particles, can't be in the same space at the same time. And there's also something called Heisenberg uncertainty principle, which says that the velocity of a particle is kind of inversely correlated with its position. So if you know where, in a precision kind of way, so if a particle is constrained to be in one place, and its movement, so its position is kind of constrained, it'll have a higher velocity. And if its velocity is constrained, then it'll have, if you know how fast it's moving, you don't know where it is, and if you know where it is, you don't know how fast it's moving. There's a nerdy science joke I think I was going to tell here, but it's fine. Anyways,
What's the nerdy science joke?
a cop pulls Heisenberg over for a cop pulls Heisenberg over for speeding. The cop asks him, "Sir, do you know how fast you were going?" He says, "I have no idea, but I know exactly where I am. I'm off the I-10 interstate." And he says, then the cop says, "Sir, you were going easily 72, 75 miles per hour in a 20 mile per hour school zone." And Heisenberg's like, "Damn, now I have no idea where I am." Okay, anyways, that's that. Get super hot. Thank you. But after that, outer layers get pushed away. The only thing that's left is the core, which shrinks until it hits that electron degeneracy and turns into a white dwarf. And it just kind of, it just kind of falls down and plops into that white dwarf place in the bottom left, where we keep all the leftover stellar remnants. And white dwarfs, of course, just kind of sit there and slowly lose their energy through radiation, which, takes a while, so we haven't really seen it happen. Okay, now stars that are mid-mass. And then, yes, finally, we get to the really exciting stuff. And kind of really complicated stuff. Oh, my bad. Sorry, I forgot about this slide. Let's run it back one more time. So our star is sitting there. It burns all of its hydrogen in its core. Currently it's being sustained by the hydrogen pressure from its core, the fusion pressure from its core against gravity. But then eventually, wow, I skipped an animation step there. Eventually it turns into a giant, the hydrogen runs out, we have a helium core, the helium core is inert, the hydrogen shell is outside, it expands, the outer layers get pushed out, it gets redder, it gets bigger, turns into a giant. Then eventually there's something called the helium flash. Finally there's enough pressure and energy for the helium core to suddenly violently implode and then fuse into carbon and oxygen into an inert core. So it moves on to something called the horizontal branch. It gets a little smaller, it gets a little dimmer, it gets a little redder. Then over time, the carbon and oxygen build up. The same deal happens. It gets on this asymptotic giant branch. We have a hydrogen burning shell, helium burning shell, and then suddenly, at some point, there's not enough fusion going on for this to sustain itself. It's run away, it is unstable, the outer layers blow itself apart, and then we're left with a core that just shrinks under its own pressure until it becomes a white dwarf. And this is what happens to us in 5 billion years. Yes, Jake?
Is the reason why there's so little points in the white dwarf category, even though like the small guys and the medium guys both fizzle out to a white dwarf, just because of time? Because they haven't been enough time to have those points, or just we haven't seen them? Or
Both. Time, and also they're very dim and slow, so they're harder to see. Yes?
How much, it feels like you could have a helium flash with carbon and oxygen if you had enough, helium and hydrogen. Is that just a larger mass star?
So,
or is that just not how that goes?
Foreshadowing is a literary device used by an author in order to, yes, we're getting there. if you have a big enough star, which we're about to, then the carbon and oxygen do the funny things. So, funnily enough, if a star is big enough, which generally these are, it actually gets a little less complicated because there's not enough time for the star to turn into a red giant because there's no like inert helium core. There's just enough mass and pressure for the helium to start fusing too. So there's no electron degeneracy. It just keeps on fusing stuff. So helium just fuses, heavier stuff just fuses, carbon, oxygen, silicon. Eventually we get to iron. Iron, it stops fusing. Not because there's not enough pressure for that to happen, but because of something called binding energy and also weird, more nuclear physics stuff. Specifically, iron is considered the most stable nucleus because with a nucleus there's a, what's it called? There are two things that determine its stability. One is, you can think of it as like the surface area of the nucleus. Like a nucleus with a larger surface area per volume will generally be larger surface area. Yeah, larger surface area per volume will be less stable. So you want a helium nucleus that's large enough so it can, hold itself together via the strong force. But then you also have the electromagnetic force, which is like proton, proton. They don't like each other, and so really heavy nuclei, the proton forces like push itself away, and so there's this weird tug of war between these two forces, and the element that wins that tug of war is iron because it's in the most stable configuration. This is a graph of the binding energies of different elements. You can see that hydrogen to helium kind of increases its energy, and then weirdly enough, it goes down again. I suspect that's because of weird electron shell stuff as well. I'm not entirely sure. But then it, pretty consistently goes up and up, and then eventually at iron, it kind of peaks off and then levels down. And so you can think of this as, that's why we have nuclear fission, because energetic or really heavy nuclei will actually give off energy as they split apart. Right? Whereas really small nuclei give off energy as they come together. So it's in a simplified way, you can think of it like that, as like there are two forces, two types of energy, and iron wins the battle because everyone wants to be iron. But eventually, iron hits something called the Chandrasekhar limit, which the goat, the Indian goat, Chandrasekhar figured out was about 1.4 times the mass of our sun. If a white dwarf hits that via like taking mass off, accreting mass off a binary star or something, it explodes in the most luminous event that we know, called the Type 1a supernova. We're not going to get into that. That's a whole other thing. But if this iron core hits that Chandrasekhar limit, then iron degeneracy, that kind of basic electron degeneracy, is not enough to sustain itself. And I don't know why I included the HR diagram. I low-key don't really know because it goes in so many different directions at this point that it's kind of not useful for us anymore. But yes, we get into shells, more stuff fuses, and we have an inert iron core. And then finally, core collapse supernova. This is so tough. Oh my god. If I started a band, this is like, okay, there are a lot of other names, but this is on the top 10 of the, what's up?
What are your other names?
I'll show you my like note stock. I have it somewhere.
Can I get like one or two that are not stuff?
Okay, this one was up there. I think there were some other weird science ones. I'll get back to you.
You are failing to name one.
Yes, because they're
on the spot.
I just want one. I just want one.
5-month-old note document I haven't touched in a while,
I just
man.
want one.
I started a jazz combo in high school, and I didn't choose the name. Let me make that very clear. But the sax player was like, you know what we should be called? I was like, what should we be called? He said, she's my friend, she said we should be called Avik and the Shitters. And I was like, what the hell are you talking about, man? And then we were for about 3 months, and then we turned into the After Hours Jazz Affair, which was an interesting name for sure. But anyways, core collapse supernova. What a tough name, what a tough event, super cool stuff happening. So what happens? The core collapses and it goes supernova. What the hell? Okay. Super complicated, we're not getting into any of that deal because there's a lot of like weird turbulence simulations and a lot of weird stuff happening. But basically, the huge ass iron core suddenly shrinks to a fraction of its size in under a second, which is like a quarter of the speed of light, which is insane. And as someone so eloquently put, it's crazy.
It is crazy.
It is crazy. It is
I
crazy.
said that.
You said that. That's
Oh,
the
and
thing.
3 people. Oh, thanks, guys.
Oh, you should see the people who responded to.
Really?
Yeah. Anyways, yeah, a lot of stuff just happens in under a second. He's right. It is crazy because there's a huge amount of energy that's released when.
Wait, with stars? Oops, I meant to say with stars. That's a typo.
With starts, we're typically dealing with billions of year timescales.
Wait, no, that's true.
And yet this happens
Billions
in a
of
fraction of a
years.
second.
Years.
Time.
Timescales of billions of years.
No, we believe
You
you.
know what I mean.
Yeah, we get it.
what I mean.
Hey, all right. Anyways,
Pull it.
yeah.
I'm trying to. I don't know.
Electrons fuse with because
The
weird,
what?
more nuclear stuff happens. Electrons fuse with protons in a process called neutronization. Something like that. They turn into neutrons. Electrons, protons turn into neutrons. Yeah, it creates neutrons, and it also creates a bunch of neutrinos because nuclear physics, whatever.
Nobody responded.
Oh, did a lot of people just like
There's-
respond to the?
Oh, I didn't like it.
Am I making something up? Maybe I'm thinking of another area.
Maybe there was another thing.
Oh, I'm thinking of another area in the book, which we'll get to. But
Am I quoted
anyways,
twice in here?
what?
Am I quoted twice in here?
No, but the book is.
Oh.
You have a
Yeah, sorry.
YouTube.
I do have a YouTube link in there.
Anyways, electron degeneracy, it reduces because there aren't, there's not enough matter that's under the specific conditions for electron degeneracy, which means the core collapses even faster. And then, all of a sudden, the strong force comes into play. So the strong force, it acts kind of like a spring. Yeah, I know, that's crazy. Yes.
So I was just curious about this, it was sort of mentioned in the book.
Mhm.
If there's not enough energy to trigger fusion, does the electron degeneracy pressure act like sort of a hard limit? How strong is the force resisting further expansion when you hit that limit if there's not enough force or heat or whatever to create fusion?
In what set? Are you talking about like white dwarf environment? Like what are you?
Basically like the core bounce. The textbook phrase is that the core bounce happened because you hit the electron degeneracy limit quickly, and then but that force caused the core to rebound and get larger all of a sudden.
As far as I thought it was you hit neutron degeneracy.
Oh,
And then the momentum of the core keeps it going until the strong force comes into play. Because the strong force is what determines forces between nuclides, which is protons and neutrons, right? And so generally protons and neutrons are held together up to a certain point. And then past that point, they're like, damn, get away from me. But like, this is around the distance that protons and neutrons are from each other. And if they're any closer, then it pushes them apart again. Which is, oh, sorry, not here, my bad. Here. This would be where the forces cancel each other out, right? Whatever.
That is 0.
Yeah, that would be 0. Anyways, point is, it acts like a spring. So the core that suddenly collapsed at like a quarter of the speed of light rebounds, called core bounce, and then collides with all the infalling matter that's also collapsing on top of it. And then all the outer layers kind of absorb the shock. So again, no reaction from that, but there's an additional pressure from all the neutrinos that are created through something called the Urca process. Again, weird stuff. Crap ton of neutrinos are created, and generally each neutrino only has like a 1 to 10% chance of actually interacting with the matter like the star that's going through. But there's just like 10 to the power of 58 neutrinos, or sort of some ridiculous number, that we actually get to see like the neutrino pressure actually has a really tangible effect, and it creates this ripple of higher fusion, where elements all the way up to nickel are actually formed in that extremely dense environment. Neutrinos, they kind of, whatever. Urca process, look it up. There's this cool video, actually, that explains a lot of this really, really well and in-depth. But anyways, the outer layers blown apart, and eventually we get to, y'all like that? Thank you. Eventually, we get to the point where it's like this diffused cloud of gas and dust, and in the middle, we have finally our neutron star. So one of these events creates a ridiculous amount of energy, like a stupid amount of energy. One of the more luminous ones was this one called Assassin 15, and it is math time. Pull out those calculators. This one's easy, I promise. So, the average star in the Milky Way has a luminosity of 5 times 7 times 10 to the 25th watts, which is joules per second, and there are 100 billion stars. So how much energy does the Milky Way produce in a second?
Maybe 2.
Yeah, at least.
TJ's law.
For
No,
sure.
no more than 4.
No, I don't know about that. I think it might be a little more than 4.
In the range of 2 to 4, not including 4. Not including.
But like 2 to 4 inclusive?
No, not inclusive.
I got distracted by AirPods falling. What was the question?
Sorry. First, how much energy does the Milky Way produce in a second? Which is just multiply the 2 numbers.
Oh, yeah, okay.
Okay, and now compare that to the amount of energy emitted by one of these events. Like just one supernova.
Pretty cool. It's a lot.
Wouldn't it actually be pretty hot? So many.
Oh, it's less.
Because we're just multiplying the 5.7 with 100 million, right?
Oh,
Yeah.
so 5.7 times 10 to the 36.
10 to the 36, yeah.
And then 2 orders of magnitude lower than one single supernova.
So, yes.
38.6 times the energy that the Milky Way produces in a second.
And that was happening for about a month. So, for an entire month, this one supernova put out about 40 times the amount of energy that the entire Milky Way galaxy, it's really hard for me not to swear, that the entire Milky Way galaxy produces.
Multiple times.
Yeah, but like, there's a certain boundary, you
Look,
know?
I'm not gonna bullshit you.
Yeah, that's like an okay one. I've heard professors say that one.
Movie ratings have like a level of allowed like instances of.
Yeah, this is PG-13.
Yeah.
Oh, wait, PG-13 allows one F-bomb. This is fucking insane! Are you kidding me? Okay. Anyways,
Damn.
it's wild. Yeah, so finally we get to Neutron Stars. I promise we are almost done, and it's been holy shit, it's been an hour.
Alright, it's alright. It's already an hour.
So, crazy objects, a lot of weird stuff about them. Huge densities, of course, because they're supported by hopes and dreams and nuclear degeneracy. There's this quote from Wikipedia, I'm not gonna lie, that's where I stole it from, that probably quoted something else. And it's just numbers. It's like, there's really no way to understand how ridiculous a material like this is, because what? But like a matchbox amount is, you know, a huge section of the cube, a cube of Earth's surface, which is really funny. Makes me think of Minecraft. But anyways, the conditions on this are so strange that it gravitationally lenses itself. A black hole would do this too, and it kind of does do this, but like no photons leave a black hole. But photons leave a neutron star, and because of that, we can see like behind the pole of the neutron star from the front, because the photons that get emitted like curve through its gravitational field, and so we can see more of the. Generally, you can only see like, you know, half of the planet at any given time, or even less, or you can see like, you know, this section of the planet, or you can at most see half the planet. Neutron star, you can see up to like I think 60-70% of its surface, which is wild. Like what?
Just like, is it longer? Like,
What is what longer? Yeah.
you just see it as like if I were to look at that.
Oh yeah.
It would just like a longer star.
It would look bigger, yes.
Bigger? Oh.
It looks bigger than it actually is. And actually, so do black holes. It's called a black hole shadow, and I guess neutron stars probably have the same thing to a lesser degree. But photons that can't leave the black hole aren't necessarily ones that go through the event horizon or touch the event horizon. There's also a region around the event horizon where photons that don't have the right trajectory will spiral in. And so because of that, like even if the black hole, like event horizon, is here, there's a shadow around it that you don't see, which I think is like 1.5 times the radius of the black hole or something. But then even cooler than that is that if the black hole's spinning, like on a certain, in a certain direction, then the shadow itself gets like distorted and looks like D-shaped. Because photons, D-shaped, like a D, like a capital.
No, I was
Yeah.
referencing that. Why would it not be symmetrical?
Because the black hole's spinning.
Right, so if it's spinning,
photons-
why would it not spin equally? Why would it not be elliptical?
The side that is spinning towards us, photons are pulled towards us, and the side that is spinning away from us, photons are both away from us. And so there's a greater shadow.
For us, what we would see.
Yes. The
side
shadow is
that's
from our perspective.
away from-
In reality, it would be.
I think so. I could be wrong. I could be very wrong. But cool stuff. Cool stuff happens for like highly relativistic spinning
Then go that way.
Yeah.
Echo fiber
And also
rays.
neutrons.
So no see that side, but see this side.
Okay, so weird stuff happens on the inside of a neutron star. We need better simulations. There's something called nuclear pasta, which is really fun.
Is it tasty?
I don't know. You should try.
Does that have to do with spaghettification?
No, unrelated, but I think astronomers just like really like gluten. So nuclear pasta is a description of the types of matter and structures that are happening inside a neutron star. There's also this weird description of like maybe it's probably like superfluid-esque, right? Like it just keeps spinning. You know, superfluids keep spinning. There's no turbulence. There's this weird description of matter called a Fermi liquid or a Fermi gas. And then at the really dense area, there's something called a quark-gluon plasma, which is another state of matter. These are all different states of matter. Forget the three. This is advanced physics. Quarks and gluons are the elementary particles that make up like protons and neutrons. So literally the forces that keep all of matter together break even those apart, and it's just this like mishmash of protons and neutrons itself being ripped apart under such high pressures. What's going on, man? So yes. Let me get through this because I want to show you the photo of nuclear pasta. This is what nuclear pasta might look like. This is a simulation.
Oh, it don't look that good.
This is what they get, and it's really funny because you get like spaghetti, but then you also get anti-spaghetti.
I like
like holes,
spaghetti.
an anti-nuclear.
Anti-joking.
Yes. Okay. This is practically like the last content slide, so let's get rid of it. Let's finish this real quick. There's a crazy magnetic field that all of these have, which we kind of talked about because reasons. Actually, I think the reasons are still kind of a little debated, but the general idea is because like a lot of the stars' magnetic field and field lines, flux and the gas that created those field lines get shrunken down, and so the magnetic field gets even more extreme. Everything gets more extreme because, of course. There's also pulsars, which TJ brought up, which are these crazy objects that kind of along the magnetic axes of the neutron star, because it's spinning really fast, or like along the magnetic axes, it emits a lot of like charged particles and also photons through weird nuclear processes. There's something called synchrotron radiation, where like an electron's taking a helical shape through a weirdly shaped magnetic field will produce photons, whatever. But yeah, the idea is that because it creates these like lighthouse beams along the ends, which you kind of saw on the previous slide, and then if it isn't aligned, if the magnetic spin isn't aligned with the actual spin, then the lighthouse beams will like, and if it's facing us, then it's a pulsar that we can see, and we get these extremely, extremely regular pulses from it, hence the name. So real quick, couple of trivia. This is Jocelyn Bell. She discovered the first pulsar like a while back. They called it LGM1. Does anyone know what LGM1 stood for? Throw like a weird guess because you might actually get it. It's not an astro thing.
Little green men.
Yes.
Really?
I'm not kidding. Yes.
Wait, actually?
Yeah.
Are you kidding me?
No.
What?
So they found the first one. I'm like, tongue in cheek. They're like,
What?
Little green men. Because
What?
it's
I pulled that out of my ass.
no, absolutely. That's actually what it's called.
Yeah, that's what it says.
You're kidding me.
No, so Little Green Men, because it was this extremely regular pulse, like ridiculously regular. And so the idea, at this point, our understanding wasn't of physics and stuff, where it wasn't advanced enough to think that these things really this didn't come out of nowhere. I guess we kind of knew about it. But they called it LGM because like, ooh, could be aliens. I don't think they really thought it was aliens, but it was really strange to get these extremely regular pulses, radio pulses. Also, pulsars emit radio radiation as well, and radio is what we use to send signals out into the universe. So we're like, oh my god, holy crap. Anyways, she didn't get a Nobel Prize. She was the grad student at the time, and her PI got the Nobel Prize along with someone else. He and someone else, I forget who, got it for contributions to radio astronomy, and this was a pretty big damn contribution to radio astronomy, and one of her coworkers was like, she should have gotten the Nobel Prize, but she didn't. But I think that Contact was based on her, if I remember correctly. Do y'all know Contact, the movie Contact? Love that movie, it's a great one. classic astro thing. Radio astronomer finds signals from space, like the encoding the prime numbers in binary or something, and she's like, holy crap, aliens. The ending is something. But the actual story is really good. It was written by Carl Sagan, who's like the best. But anyways, Nobel Prize. Also, I forget if we learned this, like actually learned this, because we talked a lot about it, a lot in that class. But the first exoplanet was discovered because of these extremely regular pulses, because we detected certain variations in these pulses, and we were like, oh, it's caused by a gravitational body, which is about the mass of a couple times Jupiter, which could only be a planet. So the first exoplanet was discovered using this technique. And there's also this idea of pulsar timing arrays, which are basically, do y'all remember LIGO? Oh, we haven't done LIGO yet. Okay, I forget if we went through it in this class or not, but like at some point someone's gonna give a presentation about it. But basically, by like sending light beams and like recording the distance and the time that they travel, you can detect gravitational waves because gravity shrinks and squeezes space and screws with time. And you can use those variations to detect gravitational waves, which we did. There's also something called LISA, which is the one that we're gonna throw into space, which is gonna be even better at it. But then there's an idea called the pulsar timing array, which uses these extremely regular pulses to calculate gravitational waves. Okay, finally, this is the last thing, I promise. Do y'all recognize what this is?
Flux versus time.
Yes.
1919.
It's a light curve of Jocelyn Bell's pulsar. Why is this important? You might recognize it in a little bit. So
Is it flux?
this is over like a long period of time. If we zoom in to one section, it still looks okay, like a bunch of pulses. I get it. Whatever. What's the deal? If we zoom in even more. Okay, what did we learn from Tansu's class? What do we do with the light curves? We fold them. Say again? Oh, what did you say? Oh, never mind. Okay, we fold them. So let's cut them apart. Let's stack them all on top of each other.
Yummy.
What the hell is this? Doesn't really say anything. I have an idea. What if we, instead of folding them directly on top of each other, kind of layered them, step by step? So we separate them out a little bit.
What is it?
You get something that looks like this. Does this look familiar to anyone?
It looks like that Joy Division album.
Yeah.
Does this look familiar?
Yeah.
What if we added all of them together? And this is where Joy Division got their album cover. Yeah, that's actually it. They took Jocelyn Bell's data, stacked it together, and they're like, damn, this goes tough, which I agree, that's crazy. And yeah, if y'all don't know who Joy Division is, go listen to them, because they're a cool rock band. Unfortunately, they are British, but you know. And then, yeah, all right, finally, black holes. I'm just kidding, we're not going over that. Not my job, that's someone else's presentation. And I just want to end with like another really hard quote that the textbook just threw into there for no reason.
Oh yeah.
Amazing.
I remember this one.
We are literally the ashes of long dead stars.
Did you see the poetic responses to that?
Yeah, oh my god.
I thought it would be funny, but I think I went too.
No.
Where's the emoji? I can't find. Oh, tough cold face. There it is.